So two things. I put up another extra credit opportunity. And then I'm going to put another one up here in a few minutes. So these are those extra credit token things. So if you do crappy on a quiz or a homework assignment or something like that, at the end of the semester, I'll go back through and fix bad grades with things. So if you want to protect yourself from bad quizzes, go to these extra things is the punchline. Yeah, so this is like a Bible study thing on October 13th, which is a Saturday in the morning. They're doing a study of the Psalms from Concordia Bible Institute. But in any case, if you go to this thing, it comes with lunch, I think. If you go to this thing, I'll give you an extra credit token. If the $10 registration thing is a problem, just send me a private message and I'll pay for your $10. So in any case, there's an opportunity. Then there's a thing I think next week that I have to get the details from so I can put it up, but I think it's called like Save the Night or something like that. Doctor, Take Back the Night. Do you know anything about it? Mm-hmm. Tell me about it.
So there's going to be a couple of speakers, and I know Darcy Powell is giving a little detail at one point, but I think it's about basically making our campus like aware and like, I don't know what the best way to put it, of like sexual abuse and assault and things like that.
Okay.
So I don't know how exactly it's going to look.
But something along those lines. Do you know what day it is?
No.
So I thought it
was.
Yeah. Yeah, I mean, I can go get the information. I was just saying if we had it. But I'll make that an extra credit opportunity as well. I think that's being run or at least partially organized by Dr. Tracy Tuffy. Yeah. And I'm friends with her. So, yeah, in any case, I'll make that an opportunity as well. Although we did see there's some weird signs up on campus today that I don't know. Right outside the cafeteria, there's
all the shadow people.
No. I think there was a sign that says something like 20% of all college females are. Is that what it is? Because they don't reference like where that information's coming from. That doesn't seem accurate to me, but I don't know. That's just gut feeling. I know this seems kind of like a dangerous thing to just randomly put up posters that say those kind of things, unless they're going to bring awareness to a study or something. But I guess the bigger picture is it's a problem. So if it's a problem, we should become aware of the problem and look at ways to fix the problem. But in any case, I'll have that as an opportunity. Yeah.
Question for the October 13th thing.
Yeah.
Do you have to be there the whole time, or
go
for part of it?
I would say I'm relatively okay if you go for, let's say, most of it. What was the?
Will you be there?
I'm planning on being there. That's the follow-up thing here. So next, some of you already know. I think I mentioned it in class. So next Thursday, we'll have class, but I leave that night for India for 2 weeks. We'll still have class while I'm gone. What I'll do is I'm going to record, so that'll be 4 lectures for us. So I'll record probably about a 20-minute lecture and then have homework assignments associated with it. And they'll be up on YouTube. So instead of coming to class, you'll just have to watch the lecture and do the work. I'm about 14 and a half hours ahead. I was going to maybe do classes live, but I don't know if I'm going to rely on bad India, hotel internet or whatever. So I come back on the 11th. So depending on level of jet lag, this might be a problem, but I'm planning on going to this. I think it should be a pretty interesting thing. So I have already signed up for it. So they're going to get my $10 whether I'm there or not is kind of the punchline. But in any case, I'd encourage you to go. I guess when you say part of it, you should go to most of it. So I guess, maybe at least 2 of these double quote sections. So reading the Psalms, poetry, a scripture story. So maybe at least 2 of those. If you skip the closer look, that might not be the end of the world. Something like that. So, but try to attend it. I think it'd be a good thing. There will be other extra credit opportunities, so no pressure if you can't do it. I just want to encourage you to go to some of these things, and I'm willing to bribe you with a free quiz score is the punchline. Okay. So questions, what's up?
Also, next weekend there is a hackathon in Champaign, Illinois. We, as the Hackathon Club, will be going there. All expenses paid. So if you are actually wanting to go, we have a meeting tonight where we'll be giving out information on kind of what all is going on there.
What time is the meeting? Where's the meeting?
Meeting is 8:30 in S109.
Okay, so across the hall at 8:30.
Yep.
Is the hackathon meeting, and the hackathon it's not this weekend, but it's next weekend.
Next week.
And it's called Pig Hack in Champaign, Illinois. We went to it last year. It was actually a pretty good one. They had some cool internship and job opportunity companies there. Wolfram Research was there. So it could be a cool opportunity to go do one of these 24-hour hackathon things, but also get some connections with some companies that are in the Midwest. Most of them were in the Champaign area specifically, but it's a 3.5, 4-hour drive. So I'd encourage you to take part in that too, if you can, basically dedicate a weekend to it. You're probably are you driving up Friday night?
Yeah, we'll be going Friday night.
And then coming back Sunday afternoon.
And then coming back Sunday afternoon.
Okay. Yeah. So one thing you'll have to figure out though is like if you guys how are you working hotel rooms?
So that's something that we'll be discussing at the meeting.
Okay. Because we make sure this is welcoming for female participants as well, and probably don't want to just throw guys and girls in the same room. So maybe
we're gonna pile 16 guys in the same room, and then
attend the thing next Wednesday or whatever So make sure you're thinking ahead for that so that everybody feels welcome to the event. All right. So so that's that, and make sure you post about that on Slack as well, so people have the information. Okie dokie. So let's see. Last time, where are we at here? There we go. So last time we were talking about the various ways of representing negative numbers. What are our 3 ways of representing negative numbers? Okay, and what's the difference between them? Sure.
Sign and magnitude is like the left bit, and so if it's a 1, then it's a negative number, and if it's 0, it's a positive number. Is that right?
You said 1 is a negative number, 0 is a yep.
And then 1's complement is like each one, so the 0 is 1 is 0.
Okay. But how are negative numbers represented there?
With 1 in the front.
Okay, so sign and magnitude is left bit used for sign. Rest of bits used for magnitude or value. 1's complement. How are positive numbers represented in 1's complement?
Positives are led by zeros.
They are led by zeros, but so let's say I wanted to represent the number 5 in 1's complement. So 5 in 1's complement. What would that look like?
0, 1, 0, 1.
All right, so this is the 1's place, the 2's place, the 4's place. This is a 4, this is a 1, so that's a 5. I didn't see any bits flipping. Why didn't we flip any bits? Because what?
He's got it.
All right.
You only flip bits into negative numbers.
All right, so we only encode negative numbers. Right? We only encode negative numbers. So we don't have to flip the bits if it's a negative number. So given that this guy has a 0 in the front and we're representing a positive number, no flipping is required. Okay? So we encode negative numbers by flipping all bits from 0 to 1 and from 1 to 0. And then we'll say negative numbers will have a 1 in the far left bit. All right. And then what's the last one? 2's complement? How does that one work?
Would you flip it and add one?
Okay. So really I can take this guy from up here. We'll do that better. So we encode negative numbers by flipping all the bits from 0 to 1 and 1 to 0, and then add 1. And negative numbers will end up having a 1 as the far left bit. All right, so what's the weakness of sign and magnitude?
Without trouble keeping track of time.
Same thing with 1's complement. What's the weakness of sign and magnitude and 1's complement? Go ahead.
So sign and magnitude and first complement have 2 different zeros, so we'll have like a regular 0 and then a negative 0, whereas second's complement only has the 1 0 and then has an extra space for magnitude.
I thought 0 was a negative or positive.
Well, in sign and magnitude and 1's complement, we have a positive 0 and we have a negative 0. Okay, so in sign and magnitude, a 0 is 0, 0, 0, 0, and it's also 1, 0, 0, 0. It makes sense? So we have 2 representations of 0 there. In 1's complement, the positive 0 is 0, 0, 0, 0. The negative 0 is 1, 1, 1, 1. All zeros with the bits flipped. So we have 2 representations of 0 as well. Okay, now, as he pointed out, 0 in real life is neither positive or negative, or at the very least we think it is more positive than negative, something along those lines. I think it's probably neither, right? It's the neutral one, right? Okay, but we certainly don't need 2 ways. We don't have 2 numbers in our counting system that both mean 0. We just have a single 0. So both of these guys are inefficient from that perspective. Whereas with 2's complement, we have only 1 representation for 0, and the other representation gives us 1 more value that we didn't have in the other ones for representing a number, right? A negative number. So last time we reviewed how subtraction works. Are you posting on Slack during my class?
No.
Are you lying to me right now? It's fine. All right, so 2's complement, we fixed the problem of not having both 2 representations of a 0. So we only have 1 representation of a 0. And then we are able to then gain an extra representation for a negative number. So that seems good, right? Now, the downside, though, with 2's complement is we need to learn how to subtract. And as we saw last class, we have forgotten how subtraction works. Okay, except Maddie came up and helped us, and then magically discovered how subtraction actually works, right? It's like we borrow a 10 from here, right? And then, so yeah, that's base 10. But so what do we do in base 2? We borrow a 2. That's what we're borrowing. So going away. Okay. So let's look at that again. Relatively briefly. Then we want to write a program that encodes and decodes 2's complement. You know, for fun. So that'll help us understand the stuff. All right, so as an example here, so if we're looking at 2's complement, if we have the number 8, well, here, let's start with 0. Here we'll do our nibbles, right? 4 bits like we did last time. If I want to represent a 0 in 2's complement, what do I do? Do I have to do anything?
No.
Because I only encode negative numbers, right? So that's a 0. I'm not holding a negative number. I am done. 2's complement required no hands. All right. Same thing. If I want a 1, if I want a 2, if I want a 3, so on and so forth. Make sense? Okay, so all our positive numbers are just as is. So now, if we want to look at our negative numbers. So if I have the number 1, and I want to represent this as a negative 1, the first thing I do is I flip all the bits. So flip the bits. Okay, so I have the number 1. I want this to become a negative 1, so I need to encode it as a negative number. So I'm going to flip the bits. This will be 1, 1, 1, 0. Then we add 1 to it. That's going to be 1, 1, 1, 1. Right? All right, so now if I give you that number, 1, 1, 1, 1, I ask you, what's the value of this number? First thing you might say is, it depends. You're going to need some information from me. Because if I just give you a 4-bit number, 1, 1, 1, 1, you could do the math, right? Or is it just whatever? Maybe it's not any sort of complement. Maybe it's not encoded anyway. If it's not encoded at all, this is the 8's place, the 4's place. That's a 12, a 14. This is a 15. That's 15. So if I just give you a 4-bit number, 1, 1, 1, 1, I say, what's the decimal equivalent of that? 15 is a fair answer, right? Because I didn't give you any information about whether this number was encoded. But now if I tell you it's a 2, that this is operating in a 2's complement encoding world, let's say, the first thing you would do is you would notice the far left number. Because would it be fair for me to say, if I just gave you this number here as a starting point, I say this happens to be in 2's complement, you would look at that and say the far left number is a 0, so you don't have to do anything with it. That's a 1. That make sense? So even though I've told you that I'm following the rules of 2's complement here, 2's complement says we only encode when we want to represent a negative number. Okay? So right here, if I gave you this number right here, 1, 1, 1, 1, and I happen to let you know this guy's in 2's complement, what you would have to do is you would have to flip the bits. Well, you would first subtract a 1. Then you would flip the bits. Correct? You got to go backwards. You got to decode it. If it's encoded into 2's complement, we have to decode it to get it back.
That's confusing.
Well, if I tell you that this number is encoded using 2's complement, the very first thing you would do is you would look at the far left bit, and you would say, if that's a 1, that means this guy is the representation of a negative number. Therefore, in order to get the value that's in there, I have to decode it. And decoding it means reversing the steps of 2's complement, which says subtract 1, then flip the bits. Because to get it into 2's complement, what did I do? I flipped the bits, then I added 1. Make sense?
No,
Tell me what doesn't make sense about it.
so once you said, how did you explain how to decode it now?
Decoding is the opposite of encoding. So if we are encoding 2's complement, let's just start with this. So I want to represent -1. That's what I'm trying to accomplish here. So I start off with the binary representation of 1. Then I flip all the bits to get me the 1's complement. So that's the 1, 1, 1, 0. So now I have the 1's complement version of 1. Then I add 1 to it. So I add 1 to this, to 1, 1, 1, 0. I add 1. I'm left with 1, 1, 1, 1. So this is the encoded. So 1, 1, 1, 1 is the encoded 2's complement version of -1. That's what that guy is. All right. So then if I say that you need to decode a value, decoding 2's complement. If I gave you a value 1, 1, 1, 1, and I told you that this was in 2's complement, right off the bat, you would look at it and say, the far left bit is a 1, therefore this is a negative number. Therefore, it is actually encoded. So I need to reverse the encoding. Well, the last step we did for the encoding here was to add 1. So the first step I'm going to do for the decoding is to subtract 1. So I'm going to have, so the first thing I'll do is I will subtract 1. So this is effectively going to be 1, 1, 1, 1 minus 0, 0, 0, 1. Okay, so 1 minus 1 is 0, 1 minus 0 is 1, 1 minus 0 is 1, 1 minus 0 is 1, so it's going to leave me with 1, 1, 1, 0. Okay, so that is my first step in decoding a 2's complement number. Then what's the last thing we do? Now we flip the bits. So 1, 1, 1, 0 will become 0, 0, 0, 1. Since the far left bit was originally a 1, this is a negative number. So the value is negative 1. This is the value 1. We decoded it from a value that started with a 1. Therefore, we put a negative sign and then whatever the magnitude was, which is a 1. So that's how we go back and forth between 2's complement. But we only decode if I'm dealing with a negative number. So for instance, if I duplicate this slide, why do I keep putting things all the way up here? I don't like the way this scrolls. I'm just going to roll with it for right now. Okay, so let's say that I give you the number 0101. Okay, and I tell you that this number is a 2's complement value. Okay, so it's in a number system that's governed by 2's complement. The very first thing you would do is you would look at the far left bit here. And since it's a 0, this is a positive number. Do positive numbers require any encoding? They don't. So we don't have to do anything special here. We just convert this binary number to its decimal equivalent, which is 5. And because that first value is a 0, this was a positive number. That's a positive 5. Make sense? All right, so then the one extra thing we gain with 2's complement. So 2's complement gains a value. That is, we don't have 2 representations for 0. That's the weakness of sign and magnitude and 1's complement. Sign and magnitude and 1's complement are fine for representing negative numbers and positive numbers. They're just not as efficient as they could be, because we have 2 ways of representing 0, which just seems like a waste of space. So 2's complement gains a value, and they gain it on the negative side. Okay, because the positive side, there's no encoding, right? So when we deal with the 2's complement version for a 4-bit number, when we have that 0 as our far left bit, the biggest value we can have is 111, like that, in 2's complement for a 4-bit number. And that's the number 7, correct? All right, so we gain a value though. So a 7 looks like this, a 6 is going to be missing the 1, and so on and so forth. So all of our positive numbers in 2's complement look just like those numbers in standard binary, with the exception that we've made the far left bit off limits for holding magnitude. But now where we gain our extra value is now we have the ability to store an 8. But in this case, if I'm telling you this is a 2's complement value, this value right here is a negative number, right? So specifically, this is a negative 8. So just like we did before, if I want to decode this number to get the negative 8 out of it, what do I do first? I subtract 1 from it. So we're going to subtract 1. So now how did we get our subtraction to work last time? This is where we reminded ourselves how we subtract. 0 minus 1 can't be done, so I need to borrow. So where do I borrow from? Well, I try to borrow from the dude next door. Nothing available. I try to borrow from the dude next door. Nothing available. I try to borrow from here, and I'm successful. So this becomes a 0, and what did I borrow? I borrowed a 2. Instead of a 10 like we borrow in base 10. Now I'm able to borrow here. So I borrow 1 from my 2, which gives me a 2 here. Then I'm able to borrow here. So I borrow 1 from my 2, which gives me a 2 here. 2 minus 1 gives me a 1. 1 minus 0 gives me a 1. 1 minus 0 gives me a 1. 0 minus 0 gives me a 0. This is 0, 1, 1, 1. Okay, so the value 1, 0, 0, 0 minus 1 gives me 0, 1, 1, 1. See how that borrowing worked? It's going to be pretty important because we're going to write a program that does that to remind us how. Maddie, you said first grade is when we learned subtraction?
Well, it could have been second grade, and I've just been adding in first grade.
Okay. A while ago for all of us, right? They didn't even do math when Dr. Locklear had second grade. They just had sticks and stones and chisels and stuff.
I'm pretty sure I was still coloring.
You were still coloring in first and second grade?
No, in first. Second, I definitely remember doing that. First,
No.
Subtracting in first grade.
Okay. Well, regardless when you did it many years ago, right? Which becomes kind of the funny thing here is that we all take a lot of things for granted because they're so easy for us to do. This goes back to your very first programming class, where one of the problems with programming, why it's difficult to become a programmer, is because we're so good at solving problems, we forget how we solve them. We don't even think about subtraction. Well, now with tools, we don't even think about it at all. We can just ask Siri. Why even touch a keyboard? We can just talk. Maybe, do any of you do math that way?
I really dislike
Really?
Yeah, like even or Alexa or whatever it is.
Yeah, we do it in our house. Like sometimes well, I think maybe the biggest thing is when we're trying to figure out like leaders to courts, stuff like that. You can ask Alexa that stuff, but Alexa will just do math too. I like to go between Celsius and Fahrenheit that way too. We don't need to know how to do this stuff anymore. We have technology to do it for us. So it becomes interesting how things that we think of as being so simple, we've forgotten how to do. But now we remember, right? This isn't that big of a deal. It's like, oh, that's when we did it for real. now we're using our technology for it. All right, so we subtracted 1. Then what did we do? We flipped the bits. 1, 0, 0, 0. So this is our final value, which gives us an 8. And since it started off as a negative value, it was a 1 here before when I borrowed from it, I took it away. That means we throw the negative in front of it. So there's our negative 8. So if we're doing 2's complement, what are the range of values? Here, this will be a good question. what are the range of values that will fit in 2's complement 4 bits? What's the smallest value that will fit in a 2's complement representation of 4 bits? And what's the largest value that will fit in a 2's complement version of 4 bits? 2's complement. If we're just talking about 4 bits.
-8 and 7.
Okay, -8 and 7. So this is -8 to +7. That's the range of values that can fit in there. Okay? Now, what if I change this to say 1's complement? Now it's -7 to 7 with an extra 0. So 1's complement would be -7 to 7 with an extra 0. Same thing with sign and magnitude. But for 2's complement, -8 to +7. And we've seen values like this before because, like, when we look at the space for a byte, so a byte is 8 bits, right? So if we change this guy and say 8 bits or 1 byte, we had a -128 to a +127. That's the range of values that fits inside of an 8-bit representation of 2's complement values. So what is a -128? It's 1, 2, 3, 4. 1, 2. Okay, so that is a -128. So what do? We flip all the bits. Well, we subtract 1. So there's this number with 1 subtracted from it. So I borrowed from the far left. Then trust me, this is the rest of the value. Then I flip the bits. 1. I'm left with that. This is the 1's place. The 2's, the 4's, the 8's, the 16's, the 32's, the 64's, the 128's place. So this is the number 128. It started off as a 1 in the far left here, so it's a negative representation. That's where our -128 came from. That make sense? Okay, we can do the same thing if we go up to 16-bit numbers. Put a 1, followed by 15 zeros. That's your representation of -32,768. Make sense?
Yeah.
Okay. So it's the exact same pattern. So this is our new version of converting between a base and decimal and a decimal to a base. We have 2 patterns for that, right? No matter what the base is, no matter what the base is, the way we convert from a base to decimal is the same pattern. The way we convert from a decimal to a base, no matter what the base is, it's the same pattern. Now with 2's complement, doesn't matter how big our bit space is. Whether we're representing 2-bit numbers, 8-bit numbers, 16, 32, 64, choose your poison. It's the exact same pattern. Okay, and we're going to do this programmatically. All right, so the first thing we need to do, let's see, do we have a preference? Do we want to do a program using normal Eclipse, or you want to do it in Android? We're ultimately going to be writing a ARM interpreter or a leg interpreter in Android, so would it be beneficial to practice some Android stuff first?
Yeah.
Because Manny, you really like Android, right? I remember you said it's your favorite.
It's my favorite.
It is your favorite. Oh, so
I don't even know if I have to put on this and that.
well then, maybe just use Notepad. You don't have to use Eclipse. You just write Java in Notepad.
Sounds good.
All right. So did we decide Android would be beneficial? since we're going to be going in that direction anyways. All right. The next question is, do I have Android on here? I might start the download of Android. I got it. I wonder how old it is. Let's see how old this is. If you don't already have it, you go to developer.android.com.
I never deleted it.
So it's developer.android.com. That takes you here. Then you choose Android Studio up top here. And then go build whatever or download the newest one. It looks like 3.1.4 for Windows. It's probably ballparky same for Mac. Doesn't matter what kind of machine you have. When you first open it, it's, let's see, tip of the day, whatever. There's an ID and plugin update. I'm not actually going to do this right now, but the next time I open it, I'll do this. But if you have an update for yours, just go ahead and update it. But it just might take some time. So between now and next class, when you do this homework, I don't care if you do it in Eclipse or if you do it in Android, but it would probably benefit you to do it in Android. Let me see if I can get this text a little bigger here. Is that big enough? Can we read that, or we go a little bigger?
Looks fine.
Looks fine? All right. So, in any case, we are going to go ahead and we're going to start off by reading in a binary value. All right, so we'll just do a quick reminder of how layouts and stuff work. So actually, let me just start a new project here, just for the sake of, you can see how it works. So I'm going to say new project. We're going to call this guy two's complement. And I'm just putting it in my two's complement folder here. So put it somewhere where you'll remember it. Preferably on your machines, put it in like your Dropbox folder or something like that. So when it automatically gets backed up, I'm going to hit next. Make sure it says phone and tablet as your selected thing. Minimum API. The default is API 15. That's fine. That'll run on 100% of the devices. Don't worry about that. Just make sure it says phone and tablet. Hit next. Then always choose an empty activity as your starting point. Hit next. Main activity is going to be our main program, so just leave that alone. Make sure it says generate layout file. It should be the default. And then choose activity main as your layout name, which it doesn't have to be that, but just let the default sit. And go ahead and make sure backwards compatibility is turned on, even though it won't matter for us since we're only going to be running this in the simulator. So go ahead and hit finish. This will launchy the thingamajiggy here. All right, so here's the new program I just created for me. I'm going to go ahead and run this real quick. Just if I click over an activity main here, it's still building my Gradle thing. It should end up showing up what this thing looks like. Big money. All right, so my interface should look like it has hello world on it like that. So I'm going to go ahead and hit play here. It's going to pop open my deployment thing. I already have a device on here called Pixel API 26. If you don't have one, just click create new virtual device. I would choose like Pixel. Pick one of the phone devices, Pixel. Hit next. Choose a version that you already have installed. So I'm running Oreo here. If all of yours say download next to it, choose what you want, but you can pick Oreo here as your download for API 26. That's what mine guy already has. So if you want, just download that. It might take some time, so do it overnight or something. But ultimately, you'll just hit next, and that'll create a device that looks like this. So I'm going to hit OK. I'm also going to select use same selection for future launches. So I'm going to use this fake Android device to launch this guy. So hit OK. And now it should start launching my Android emulator. And there's my Pixel. Note 9's bigger. The Pixel is on the screen, just barely though.
Oh, that looks pretty big.
Yeah, it's bigger on there. That is true. There's my Hello World program. So if you get to this point with a brand new Android project, that means that your Android emulator and all that jazz is all working. All right, so that should be your first goal for your setup at home, is to get these guys working together. Okay, so now what I'm going to do is I'm going to give myself a quick little interface, just like a text box to enter in a number, a label to output something, and a button that I can click for it to do its magic. All right, so I'm going to come in here to my activity main. I'm going to actually dump this label here because I don't like using it and I suck at making interfaces. So even though my base component tree says constraint layout, I'm going to immediately throw a vertical linear layout in there. And then I'm going to just stack some components. So I'm going to go ahead and under text, I'm going to say we're going to enter in a number keyboard should work. So I'm going to put a decimal number thing in here. And then I'll put the hint, enter binary number. Okay. Then I'm going to throw a button in here. So I'm going to click on buttons. Just a normal plain Jane button. Drop it into my linear layout. I'll actually put this button below that guy. All right, I'm going to change the text on this button to say convert to twos complement. All right, and then lastly, I'll go ahead, I'm going to put a text view, which is like a label. I'll drop this out there. And this is going to be like where my answer is going to show up. All right, and I'll just put, so I'm going to call this guy, I'm going to change its ID. We'll call this guy answer TV. I'm going to make the text here say the answer in twos complement, something like that. All right, so the idea is here, they'll enter a binary number up here, they'll click this button and it'll, behind the scenes, convert it to twos complement, spitting the result out here to this label. All right, so let's just make our button and stuff work for a few minutes. All right, I'm going to go ahead and give my edit text here. Instead of naming it edit text, I'm going to call this guy input ET, or input edit text. All right, so now I'm going to have to go back over to my main activity. I'm going to write the function that will be associated with this button. So I'll come in here. We're going to write a public void on button pressed. So actually, let's call it on convert button pressed. This guy will take a view as a parameter. And then I'm going to go ahead and give myself programmatic access to my label. What did I call that guy? Answer TF or something like that. So this will be a private text view answer TV. And then inside here, we'll say this dot answer TV is equal to the text view version of this dot find view by ID r dot ID dot answer TV. So now I have access to that answer text view, and then we'll go ahead and just say answer TV dot set text. We'll just say worked. All right, so once this is all working, the idea will be we click the button, it will set that text view to say work or worked, letting us know that our button clicky is functioning for us. All right, I'm also going to go ahead and give myself access to that edit text. It's going to be input ET. This dot input ET is equal to the edit text version of this dot find view by ID r dot ID dot input ET. All right, so for when I need that input ET, it'll work. So let's test it once. So I've set up my code here. This is MVC. So I've given myself programmatic access to these guys by looking up their ID using the R class here. I'll come back over to activity main. I'm going to click on my button here. We're going to go to his on click property, hit the drop down, and we notice we see our thing that says on convert button pressed. That's our function we wrote. So now I'll go ahead and hit play. And it's saying, do you want to still use this connected device? I click this checkbox, hit OK. So now when we click our button, it should show the, should say worked in our text view. All right, so we click our button. There it says worked. All right, last thing we'll do is we'll go ahead and grab whatever we type in up here and have it set the label to that, just proving that we have all our pieces working together. Okay, so I will go to main activity. So I'll go ahead and say string the binary number is equal to this dot input ET dot get text. That actually gives you something called an editable. So I'm going to say dot toString to get the actual string from that. So this will read in the string from that input edit text. So I stored it in a variable called the binary number, and then I'll go ahead and set my TV equal to the binary number. So this should let us type something into the edit text, hit the button, have the output go onto the label, showing that our three widgets are working together. All right, so I'll type some stuff in up here, convert to 2's complement, click it better, and there's our number transferred to our label, text view. All right, so a couple things we can do here. One thing is we want to have the ability to flip the bits. So we're going to start with that piece of it. I'm going to actually do one other thing here. just for the sake of argument. So I'm going to throw a little switch on there. Store as negative. And we're going to call this guy negative switch. Okay. And so that way, if we want to do it as a negative number, we'll hit this little switch thing and that'll give us the representation. Well, it'll tell us that we want to do a negative number. So let's go ahead and hook our switch up then too. Private switch, what do I call it? Negative switch. And we'll go ahead and hook it up here. So this dot negative switch is equal to the switch version. I don't know if I've ever used a switch in this dot find view by ID r dot ID dot negative switch. All right, so we have that. And let's ask a question here. If this dot negative switch dot like an is activated. That looks like it could work. So if it's is activated, we'll put our number out there. We'll concatenate to it as a negative. Else as a positive. Just see if our switch works. So the idea is that when we put the switch on, we say we want to store this, we want to show this guy as a negative number, which means we need to encode. We have the switch off, it means we want it a positive number, so there's no encoding necessary, just put it out there. All right, so let's make sure our switch is working. And I'll give you this on GitHub as a starting point. All right, so whatever. I'll hit my switch, convert to 2's complement. So this is as a positive. So if I click it off, all right, that guy doesn't seem to actually get set. Is checked. Let's try that instead of is activated. Otherwise, a quick Google search might be in order. There's our negative. There's our positive. All right, so we have a switch that says whether or not we want to store this guy as negative or positive now. Okay, and we're doing this for 2's complement. So down here, if it's not checked, then our actual final answer is going to be unencoded, right? All right, so if I put in a big binary number like this, and I say that I want to, because we're not necessarily padding this out to a certain number of bits, this guy just has a magnitude. So we're saying if we're not going to select it, that means we're storing it as positive. The 2's complement version of this number is this number. So when I hit convert to 2's complement, there's the number itself. Otherwise, if I have this guy selected and I say convert, then it has to do the 2's complement function. All right, so we need to encode this guy as 2's complement. All right, so we'll have this guy, let's actually have him return a string. We'll have him return the encoded version. All right, so if our negative thing is checked, then we want to go ahead and call encode as 2's complement on our number. So here's our binary number. So we'll say this dot encode as 2's complement, the binary number. So our encode as 2's complement is going to call this function right here, which is going to do our magic, and then it will ultimately spit out the string that should be the 2's complement version of this guy. So just for starters, let's go ahead and just make it return our binary number. We won't do anything to it, but just making sure all our pipes are working. So we're calling our function. Our function is just spitting the string right back to us and saying, I'm done. And even though he hasn't done anything, and then we're going to put it in our box. Okay. So go ahead and run this. Make sure we don't get any weird behaviors, and then we will start writing some flip stuff. So put some values here. We're going to say we're going to store this guy as a negative. So now when I hit the button, it's going to send it into our encode in 2's complement, which is going to set the value back out unchanged. So there's our value. Not a great way of testing this work because it's the same value in and out, but regardless. Yeah. So in any case, we want to start writing our logic here in encode as 2's complement. Now, the very first thing we do when we encode in 2's complement is to do what? We only do two things. What's the first thing we do? Flip the bits. So flip the bits first, then add 1. That's encoding. Decoding is subtract 1, flip the bits back. Right? All right. So I'm going to write a little function here. Let's break this into individual functions. So string, call this guy flip the bits. And for the sake of this assignment, you can probably, you don't have to check to make sure they've put in legal binary numbers. You can assume they've given you 0s and 1s. You know, so if you typed in hello for your number, it should not be a big fan, and it's fine if it crashes. All right, so we're going to call this guy flip the bits, and his job is to go in and create a new binary, a new string that is the same length as the original string, where every 0 is a 1 and every 1 is a 0. Make sense? All right, so we're going to say string answer. Starts this guy off as the empty string. Create a for loop. And we'll go through, we'll ask what the current character in bin looks like. And if it's a 0, we'll make it a 1. If it's a 1, we'll make it a 0. So if bin.charat I is equal to the char 0, then we want to concatenate onto answer the char 1. Else concatenate onto answer the char 0. Finally, we're going to return answer. So this function should flip all the bits. Zeros become ones, ones become zeros. So rather than just returning bin here, let's go ahead and we'll give ourselves a variable. So string, call this bits flipped, is equal to this dot flip the bits of bin. And then we'll go ahead and return bits flipped. So what are we actually returning here? What kind of animal are we returning based on what we've learned about ways to encode negative numbers? This is the ones complement. Okay, so we've produced effectively the ones complement at this point. Okay, so encode is 2's complement. First thing we do is we ask our flip the bits function to, we pass in our string. It should go through and flip the bits. Then we'll return bits flipped. And what are we doing with that? We're going to set our answer TV equal to that. So now we should be able to tell the difference between those two guys based on what the, if we don't have it selected as negative, it's just going to be the regular number. If we do have it selected as negative, we're going to have the regular number with all the bits flipped. Go ahead and run this. All right, so 1 0 1 1 0. If I leave that box unchecked, it's just going to copy it across. If I check the box and do it, it flips the bits. All right, so bits are now flipped. So now we need to do some math. So we need to add 1 to this guy. Just a real quick thing we could have done here. I think this will work for this. So answer plus equals bin.charat I equal 0. If you want a shorthand version of doing that flip the bits thing, you could have done that. So let me run it real quick and I'll explain to you what that is for those of you who don't remember inline if statements. All right, so bits are all flipped. All right, so you don't necessarily see this in the wild very often, but this is a reasonable example of where you might use an inline if statement. So I'm building up answer here. So I'm saying answer is equal to answer concatenated with. So an inline if statement has a Boolean expression followed by a question mark, followed by the value it should boil down to if it's true, followed by the value it should boil down to if it's false. So if the character I'm currently looking at is a 0, this expression right here should boil down to a 1. If it's not a 0, it should boil down to a 0. So this allows me to have a one-liner for flipping the bits rather than going through and having the if statements, even though they logically will accomplish the identical thing. Does that make sense? All right, so I would call this a relatively reasonable use for a inline if statement because we did really save quite a bit of almost like curly brace jumbling, having an if and an else that didn't really do much other than just go from a 0 to a 1. All right, so I'll leave it like this just as an example. If you never use an inline if statement in your entire life, that's okay. It's not a problem. There's plenty of people, plenty of programmers that might go their entire career and don't use inline if statements. Do you find that you use them very often? You really do?
Yeah, I think they get used a lot more, especially if you're doing front-end stuff like web development, because especially like if you're using Angular or something like that, it's a lot easier in the template.
Yeah, I get it.
A lot of times you only compare is the value
this or that, and whether or not something should be checked or whatever.
Yeah, you're not usually doing a ton of multiply things, so it just makes it a little cleaner.
Yeah, I didn't think about that for front end, but that makes some sense. All right, well, there's your syntax for an inline if statement. Not too bad, just looks funky when you're used to seeing if statements, right? Okay, so that's our flip the bits. All right, so now we need to add 1 to this guy. So private string add 1 takes a string binary in as a parameter. And what does this guy do? He is going to add 1 to the binary number that you just passed it. But how? So when we add 1, so this guy will add, will return a new string that is the given string with 1 added to it. All right, so that's what this guy will ultimately do. For right now, I'm just going to return bin, so it won't throw an error. All right, so this guy, we say add 1 for encode as 2's complement. The first thing we do is we flip the bits. Then we're going to have 1 added, and this is going to be equal to this dot add 1 of whatever came out of flip the bits. And then we'll return 1 added, because that is our final 2's complement value, right? All right, so then down here, we're going to encode as 2's complement, passing it the number, which comes in here, and it flips the bits. Then it adds 1. Then it returns that thing. What do we do with it? We set the text for our answer to that value. All right, and this is reliant on our add 1 working. So for right now, I want to go and check this into a GitHub, so I have the link to give you. And then let's spend a couple, because we're out at 25, right? Okay, let's spend a couple of minutes thinking about the algorithm for what you will have to write in here. So your homework is to write add 1, to do that part of this. All right, and if you've never used GitHub before with Android Studio, just as a reminder, well, here, let me just do this part real quick. So I'm going to go to that. I'm going to say check into version control, GitHub. Oh, that seems terrific. Does Git really not come installed on Windows? That seems to be problematic at best. So I'm downloading Git here for Windows. I would have thought so, but all right, I just agreed to everything, basically, and then we're going to hope for the best that it could find git.exe. Otherwise, I'll just zip this project up and put it on Slack so you can just use it as your starting point. But the issue is Android Studio is relying on me having Git installed on the machine, because that's what it's using to create the repository and push it up to GitHub. And it couldn't find git.exe because it wasn't installed on a Mac. It's installed by default. I just presumed it would be on a Windows machine as well. Okay, I don't want to view your release notes. Let's go back in here. Share project on GitHub. I'm going into my environment variables. Let's go to path. Go to edit. Go to new. Go to browse. Should be in git bin. Hit OK. Hit OK. Hit OK. Might have to relaunch this guy here. Let me close this and reopen it so we can find that. I'll just do it from out here. Close. Import. All right, so it seemed to recognize it now, so you need to make sure you add it to your path. So I'm going to click on login. Oh, I have an account. Password. There we go. So you log in with your account on here. Unauthorized, bad credentials. Actually, isn't your email address you log in with? All right, so it's going to create a new repository called Two's Complement. Hit share. This is going to give me the link. Initial commit, hit OK. Link should pop up here in a second. All right, so here's my project. This is what I'll put on to Slack. The very first thing you want to do when you go to GitHub following this link is you want to fork this project. That will create a duplicate of the project that you own. That way you can then check it out from GitHub and make changes to it and then upload it. Okay, if this is your first time working with Android Studio, maybe get on Slack. Most of the other people in the class have had Android Studio before, have worked with GitHub. So I think there's probably 2 or 3 people in here who have never done that. So get on Slack, do that. Otherwise, you can just download the zip from this and make changes and upload your solution. But preferably turn in the assignment on GitHub so I can click the link and go to your repository. All right, I'll post this link up on Slack. All right.